Okay, and you can see it. All right, so yeah, I'm going to talk about the magnetic module and the test field methods module. So honestly, myself is not a extremely experienced user of the pencil code, so all those things are based on my personal experience with the code. So just please correct me if I said anything incorrectly. Um, so first, about the magnetic module. So the pencil code solves the vector potential rather than the magnetic field itself. This has the advantage of that the divergence of the magnetic field is ensured to be zero. So the equation to be solved is in the Weyl gauge. The Weyl gauge means the scalar potential phi is taken to be zero. So you just solve, so B here is the curl of A, and mu zero times J is the curl of B. The unit of the magnetic field is basically in the alpha unit. So the pencil code is extremely versatile, and there are a lot of possibilities. For example, you can turn off the Lorentz force on the Navier-Stokes equation. This is not something naturally happens in nature, but it's sometimes interesting to do such experiments. So by using this option, you don't have the J cross B term in the Navier-Stokes. You can also force this the magnetic equation, or you have hyperdiffusion or hyperresistivity rather, and many other things. So in the F array, this vector potential is stored here from index IAX to IAZ if you want to do some coding. So recently, it becomes possible to doing a different gauge, as Axel has mentioned on Wednesday. That is the Coulomb gauge. In Coulomb gauge, the divergence of A is zero. So if, say, the difference between the Coulomb gauge AC and the Weyl gauge AW is the gradient of some scalar field lambda, then we can take the divergence on both sides of this equation, and then lambda can be solved by solving Poisson's equation. You take divergence of the Weyl gauge and take the inverse of the Laplacian. So to turn on this possibility, you can say L Coulomb equals true in start.in. And also, you need to add two auxiliaries, and they have to be communicate auxiliaries, because when solving for the inverse of the Laplacian, you really need the global information. So those variables has to be global variables communicated between CPUs. We need two auxiliaries because one is for the divergence of the Weyl gauge, the divergence of the vector potential in Weyl gauge, the other one being the lambda itself. Then lambda is calculated and stored in the F array at ilam. But note that even if you turn on the Coulomb gauge, the vector potential itself is still in the Weyl gauge. So to do any computations in the Coulomb gauge, you need to do that by hand. Namely, when you compute, for example, the helicity density, you take the difference between the Weyl gauge and the gradient of this lambda field, and then you get the Coulomb gauge. This Sahel has already mentioned that BB and JJ, by default, they are not stored in the F array. Only the vector potential is stored. So if you really want magnetic field and current density to be in the F array, you can say you can make them as auxiliary variables. So basically, you say LBB as aux equals true, and you add a corresponding number to the C param dot local. In this case, I'm turning on both BB and JJ, so I need 6 extra auxiliaries because 3 as a vector, BB needs 3, and we have 2 vector fields, so that's 6 in total. And also, even if you turn on those 2 switches, they will not be written into the var files. And if you want that, you also need to say I'll write auxiliary as true in start.in. Initial conditions, there is a very long list in magnetic. Sorry, there's a typo here. In magnetic.if19, and please check that. There's a variety of possibilities. Right, and we also have different diagnostics. Those are specified to be specified in print.in. For example, we have the RMS magnetic field. Here, angle brackets means average over the volume. We have the mean magnetic helicity, A dot B. We have the mean current helicity, J dot B. And then we also have this one, for example, BMX. You first average the magnetic field over the YZ plane, so do a horizontal average. And then you take the RMS value of that over the X direction. So this will be useful if you want to study, for example, a large-scale dynamo. Then you look at those quantities. Those are proxies of the mean field in the box. Sometimes you also want the spectra. Then you say AB, for example, AB spectra equals true, or JB spectrum equals true. So using the first switch, you will have 2 files in your data folder. One is called power_mag. This will be the power spectrum of the magnetic energy. So B squared over 2 is this power mag. And at the same time, you have power_mag. This will be the helicity spectrum of the magnetic field. And similarly, if you say JB spectrum, you will have J squared over 2 for the power spectrum file, and J dot B for the helicity spectrum file. And there is one thing to note here, that the power spectrum has already been normalized by a factor of 2. So if you integrate over the spectrum, you get B squared over 2 rather than B squared. Whereas if you integrate over the helicity spectrum, you just get A dot B rather than A dot B over 2. So there's this difference in the code. Yeah, that's basically all about the magnetic module. And then I go to the test field methods. So if you work in the area of dynamo theories, then you know those stories of the turbulent transport coefficients, and this test field method is a way to extract those transport coefficients. So we have a bunch of possibilities here. We have not only test field methods, which is for dynamo theories. We also have test scalar fields. Like if you want to study turbulent diffusion of a scalar field, they are also possible there. Basically, you have 2 choices for the test field method. One is the quasi-kinematic test field method. For example, test field X, XY, XZ, and Z, those are all quasi-kinematic ones. And there is also the compressible test field method, which is this test field compress Z. So the difference between the quasi-kinematic method and the compressible method is that it depends on whether you have a small-scale dynamo in your system. If you want to study a kinematic dynamo, then you can use the quasi-kinematic method. So that means the main run can be a hydro run. That is, you don't have any magnetic field in your main run, but you only put in magnetic field in your test field problem. That's possible. Or you are really doing a MHD simulation, but it is at some low magnetic Reynolds number. So you still don't have a small scale dynamo. In this case, you can use the quasi-kinematic method. When you have high enough magnetic Reynolds number, then you will really need the compressible test field method. And here I have a few references. The nonlinear test field method is something like an intermediate step between the two methods. So how to really use those modules? Of course, you need to turn on those modules first in the makefile.local. And then you also need to register auxiliaries. And the number of the auxiliaries depend on what method you use. For example, if you look at this file, testfield_z, it has a few lines of the example. You just put those numbers in your cparam.local. So in this case, you will need 12 auxiliaries because you have 4 test fields, and each of them is a vector field. So you have 3 times 4 equals 12 total number of auxiliaries. For the compressible method, I think it's much more, the number is much larger than this. It's 26 or something. So if you run a compressible test field method, it will be much slower and you will need more CPU hours to do that. Then you put in the parameters. For example, in start.in, you say LU cross B as auxiliary equals true. And in run.in, you specify a few parameters. So here, the first 3 relates to the resetting of the test field, and this will be clearer very soon. So basically, this means you reset your test field every 30 time units, and you reset it to have this amplitude each time. Then the next 2 lines, I test field and K test field, this will specify what type of test fields you want. You need to look into the source files to see what really this means. This means you have like what types of cosine sine fields you want to put in, and this just specifies the wave number of those test fields. If you use, for example, test field XY or XZ, then you will also need to specify the wave numbers in different directions, KX and KZ, and so on. And finally, you have a magnetic diffusivity. So this basically specifies what is the diffusivity in a test field problem. And in principle, this can be different from the main run. Then in print.in, you put in your diagnostics. So the first 4 here, they mean the amplitude of the test fields. Then the next 4, this is the alpha tensor. If you're not familiar with dynamo theories, this is just the turbulent transport coefficient in the mean field dynamo equation. And also you have the eta tensor, which is the turbulent diffusivity tensor in the mean field equation. What exactly are those variables? It depends on what method you use. If instead, let's go back, if instead you have used the axisymmetric method, you will have different diagnostics. You will have alpha parallel, alpha perpendicular, and so on. And if you have the test scalar method, then you will need to put in like kappa, which is the turbulent diffusion for a scalar field. All right, so then if you compile and run the code, you will see this in your time series. So you see those columns, the B11 RMS and so on. We have alpha 11, alpha 21, and eta. So those are in your time series thing. And if you plot them, you see something like this. So first, this is the time series of B11 RMS. Basically, what you see is you see first a growth of this test field, test field, and then we reset it to some very small amplitude, and then it grows, we reset, and so on. So this interval of resetting is something you can put in by hand. Why we need to do this? Because in this case, this example is I want to study a kinematic dynamo. That means we want to keep the magnetic field dynamically unimportant. So we want to keep it small. That's why we reset it. If we don't do that, it will grow, perhaps it will grow to some very large values if your magnetic Reynolds number is somewhat large. That's why we have this resetting mechanism. On the other hand, if you look at any one of the turbulent transport coefficients, you see something like this. It will first grow, and then it saturates at some value. And notice that this is in log scale. Sorry, this is in log scale. So if you look in linear scale, it perhaps will grow somewhat linearly by a factor of few, but in log scale, it has already saturated. So what we want to do is we really want to extract the part in the time series where it has saturated. And this will correspond to some exponential growing phase of the test fields. So then you can do an average over those values as I marked in red, and you calculate, for example, the mean and the standard deviation, and that becomes your turbulent transport coefficient. Yes, and that's basically what I have for those two modules. And please ask me questions.
Yeah, thanks, Hongzhe. If anyone has any questions, clarifications,